I'm Norman Wildberger, and in today's lecture we're looking at two-dimensional geometry from the point of view of the dot product. So the dot product is this association to two vectors in two-dimensional space, a number. So x1, y1 dot x2, y2 is the number x1 times x2 plus y1 times y2. So given a pair of vectors, we get a number. This is called a symmetric bilinear form because the two basic properties of it are that it's bilinear and that it's symmetric. It's a symmetric bilinear form, and we'll see later on that there are other symmetric bilinear forms that are also quite interesting. Alright, so in this video and in the following one, we're going to have a look at how this dot product helps us set up and understand various basic things in two-dimensional geometry. So we're going to talk about lines, linear functionals, and then projections, reflections, rotations. Okay, so today we work in the planar case. But one of the advantages in this linear algebra setup is that things generalize relatively easily. So once we've understood the planar or two-dimensional case, it's usually not too much work to extend to 3 dimensions and to higher ones. And it's also not too much work to extend to situations where we work with some variant on this symmetric bilinear form, in particular the relativistic kind of dot products that are so important for 20th century physics coming from Einstein's theory of relativity. The notion of a dot product allows us to introduce, relatively simply, the idea of a linear functional. It's a very interesting, important idea in linear algebra. So if we fix one of the vectors v and w, then this dot product can be interpreted as a variable that depends on the other one. So for example, suppose we fix v, and that's a fixed vector, and then we think about w as varying. Then this dot product defines a linear functional on v2. Let's give an example. So suppose that the vector v happens to be the fixed vector 3, 2. If we dot it with an arbitrary vector xy, then the dot product is 3 times x plus 2 times y. And we can think about this as being a function which inputs the vector xy and outputs a number. So we can write it this way in terms of functional notation, or in terms of linear transformation type of notation, which it actually is. So it's taking the vector space, in this case v2, and sending it to a number, which I'll denote by f. This is a field that we're working in, which for us most of the time is the rational numbers. And specifically, this is the function. It takes a vector xy and it outputs the number 3x plus 2y. And let's see how we can imagine that particular kind of function. Here's the plane, xy axes as usual. And now I can represent this function by describing its level curves, which turn out to be level lines. So here, this line here, is the place where the function has value 0. So for all of the vectors whose endpoints are along here, the function has a value 0. If we move over a little bit here, then the function has the value 1 on this line. The function has the value 2 on this line, 3 on this line. If we move in the other direction, we get -1, -2, -3. So we can see that as a function on the plane, this is a function which is sort of moving linearly up as we go in this direction, moving linearly down as we go in this direction, and it's unchanging if we move in this direction. It's a relatively simple kind of function whose gradient or whose direction of greatest increase is along the vector 3, 2, which is the vector that we started with over here. Okay, so this is actually a linear transformation from v2 to f, because it's just given by linear expression in x and y. And so it has a kernel. So if we ask, well, what vectors x, y get sent to 0, we're just talking about this line here. And it's the span of the vector minus 2, 3. If we put minus 2, 3 in here, we do in fact get 0. And of course any multiple of minus 2, 3 is also in the kernel. All right, so the vector minus 2, 3 is this one right here. It's perpendicular to the vector 3, 2. And it spans the kernel of this transformation. And the level curves, or the lines that I'm drawing here, are always parallel to this kernel. This is called a linear functional on a vector space. It's a particularly simple kind of function. It's a linear function. Has the value 0 at 0. And it's basically determined by one direction. In this case, the vector 3, 2, which generates the functional by the dot product. So somewhat more generally, if our vector v is the fixed vector AB, and we're still looking at this dot product v dot w, thinking of that as a functional which inputs w and outputs that number, then that functional depends on the vector v. So we might call it actually f sub v. All right, so f sub v of w is by definition v dot w. And specifically what it is it inputs the vector xy and just outputs the dot product of v and xy, which is a times x plus b times y. So such a functional is determined by the vector v, which generates it. We might call that the normal vector. And geometrically on the plane, we can represent it by the lines, the level lines, f of v equals 0 and f of v equals 1. So in the last diagram I showed you lots of lines where f is 0, where f is 1, where f is 2, where f is minus 1, and so on. But because it's a linear function, this function is actually determined by only two of those lines. So for example, let's say that the vector v happened to be minus 1, 2. Minus 1, 2 up there, there's v. Then the corresponding linear functional will have its kernel here. So it'll be 0 along this line. And it will have value 1 here. We can check that. For example, the point minus 1, 0. If you take the dot product with that, you get, in fact, 1. Or the point 0, 1/2. You take the dot product with that, again you get 1. So this is the line where the function takes on the value 0. This is the line where the function takes on the value 1. And that's all what we need to know in order to be able to completely understand this linear functional. If we want to know other values, we just go correspondingly up or down. So that's the value 0, that's the value 1, then an equal distance will be value 2, another equal distance will be value 3. In this direction here would be value minus 1. Of course, halfway in between would be the value 1/2, and so on. And as an actual function on the plane, this is the function minus x plus 2y. Now suppose we shrink this vector by a factor of 2. So it's the vector now minus 1/2, 1. So it's the same direction but shrunk by a factor of 2. Now the new functional determined by this vector, which will be minus 1/2 x plus y, is still having the same kernel as it was over here. But now the 1 level curve is a little bit further out. So for example, now the vector 0, 1 is having value 1, while over here the point 0.5 had value 1. So this line here has moved out a little because corresponding to this vector getting shorter. So the shorter this normal vector becomes, the more separation between the 0 and the 1 level lines. In the other direction, if we happen to stretch the vector v by a factor 2 to get the vector minus 2, 4, then we expect that the level 0 line is the same as it was before, but now the level 1 line has moved closer to the level 0 line, so they are more closely spaced. It's like contour lines on a topographical map. Right? If you're mountain climbing, then the contour lines which are very close together, it means that it's very steep there. the gradient is high. On the other hand, if the contour lines are further apart, then it's a more gradual incline. Okay? So bigger vector means steeper increase, means the contour lines are closer together. And this function here would be minus 2x plus 4y. So this is sort of giving us two ways of thinking about a linear functional. One is in terms of the normal vector, which completely determines the functional. And another way is in terms of the kernel and where the function takes on the value 1. Those two lines also give us a complete geometrical description of the functional. Now, I've mentioned that a linear functional can be thought of as a linear transformation of a relatively simple kind. It's a linear transformation that takes the vector space that we're dealing with, which is two-dimensional space, to basically the field itself, a number, which we can also think of as being pretty close to being the one-dimensional vector space. So it's taking a column vector and outputting a one-by-one matrix, if you like. Well, if it's a linear transformation, then it should be represented by a matrix, because we know that all linear transformations are essentially given by multiplying by matrices on the left. So we should be able to write this linear functional, f of v, in terms of multiplying by a matrix on the left. And indeed we can. The matrix is just the row vector AB, which is the transpose of the vector v that we're starting with. Right, so if W is xy, then what happens if we multiply this matrix times this matrix? Well, we get AX plus BY. Technically, we get a one-by-one matrix, but we generally drop the brackets, giving us just then a number. All right, so the thing to recognize here is that these linear functionals that correspond to vectors v have matrices associated to them which are just row vectors. Thought of as matrices, thought of as 1-by-2 matrices. And these matrices are just the transposes of the vectors v that we're starting with. This introduces a useful and important symmetry or duality in this subject that we will be talking about later on. I would just like to flag it at this point to get you thinking a little bit in this direction. So currently we're working in two-dimensional space as a space of column vectors. But that was a little bit arbitrary on our part because we could have started with row vectors. It's a matter of taste, really, or convention, whether we're working with column vectors or row vectors. But now we see that this dot product is somehow mixing these two types of vectors, or maybe we should think of as it's sort of identifying them. So if we think of column vectors, say W, the form X, Y, and row vectors, which are obtained by the transposes of the column vectors, say the row vector AB, then there's really a symmetry in this situation between column vector and a row vector. And we might want to make that a little bit more explicit by thinking about column vectors, say, as being our vector space, which we're calling V2, or linear space. It's also the same as 2-by-1 matrices, essentially. And we might want to distinguish that between a separate or distinct vector space of row vectors, things of the form A, B. And maybe we could introduce some kind of notation by something like this, that we could maybe refer to the row vectors as the space V with the 2 index at the bottom, where our column vectors are represented by this notation of V with the 2 up at the top. This would make our situation a little bit more symmetrical between column vectors and row vectors, so that there wouldn't be a preference for one to the other. These are both linear spaces. Right? We can add these kinds of vectors and scalar multiply them just as well as we can add these kinds of vectors. And this dot product that we've got here is really, in some sense, connecting these two spaces, allowing us to think of a column vector like this being associated to the corresponding row vector, which is given by its transpose. I just want to introduce that idea to you at this stage here. I'll talk about that further on. It's the idea that there might be some use in thinking about column vectors and row vectors as pretty close to being the same, but as sort of separate kinds of objects that are behaving algebraically a little bit differently. Now let's talk a little bit about lines in the plane. So a general equation of a line in the plane has the form ax plus by equals c. And we can see that this can now be interpreted as a level curve or level line for a linear functional, the linear functional ax plus by, which is generated by a vector AB transpose. And so here's the actual vector AB, which we might call n, call it the normal vector that's associated to this linear functional and to this line, therefore. So for example, the line 2x plus 3y equals 4, which is this line right here in two-dimensional space, has normal vector 2, 3. Because the coefficients here, 2, 3, playing the same role as a, b here, it's associated to this normal vector 2, 3. So this is an interesting sort of interpretation of the coefficients of a line. So from a linear algebra point of view, we like to think of lines in this way. Although in calculus, where we think of lines often as graphs of linear functions, it's more usual often to think about a line as of the form y equals mx plus b. Well, we can solve for y, in this case here, just by moving the x's to the other side and dividing by 3, giving us minus 2/3 x plus 4/3. Then in calculus you would say, oh, that means that the y-intercept is 4/3, and the slope of this line is minus 2/3. But from a linear algebra point of view, this way of writing a line is much preferred because it doesn't pick out one of x and y as being preferred. Here y and x are playing different roles. While geometrically it's more natural that they be just treated symmetrically. Furthermore, this one here is a little bit less general because if say the coefficient of y here happens to be 0, then you have a hard time rewriting this equation in this form. So lines like x equals 2 are still lines in this form, but don't really fit into the story over here. And now we see another advantage in thinking about lines this way, in that if we just look at the coefficients 2 and 3, we recognize the normal vector for this line. Okay? So from now on, when you see a line 2x plus 3y equals 4, I want you to think, that's a line which has normal vector 2, 3. It's somehow associated to this vector 2, 3. In fact, it's a level curve, or level line, for the functional f of v, where v happens to be 2, 3. Another very important notion that the dot product allows us is the idea of a projection, or sometimes called an orthogonal projection. So we're going to talk about that now, the idea of an orthogonal projection. But let me say that it's important that we recognize that this structure and the other objects that we're talking about it now are only associated to linear algebra when you've already talked about a dot product or a symmetric bilinear form being added to the basic vector space structure. That's why the first half of the course did not discuss this kind of notion. It's important to get a grounding, in my opinion, of linear algebra as purely an affine geometry business, where the algebra of vectors is just in its own little world and doesn't require any kind of metrical structure. Okay? So I want to emphasize that we are adding structure to an affine space. The structure is given by the dot product. Once we have a dot product or symmetric bilinear form, then we can do a lot more things. We have a lot more notions around, metrical notions, projection notions, rotation notions, and such. Okay, so what are we talking about here? The projection P sub V of W. What is it? Well, we say it's the projection of W onto V is contained in this diagram here. So here's the vector V, which in this case happens to be the vector 4, 1. And here's the vector W, which in this case is the vector 2, 3. And what are we talking about when we're talking about a projection? We're taking this vector W and projecting it onto the vector V. So we're collapsing it down by moving this point perpendicularly down to this line through the vector V. And the vector that we obtain by doing that is this vector in blue here, the vector U. So the U here is the projection of W onto V. Okay, so this is how we encode that kind of perpendicularity. We're looking for the vector U, which is in the direction of V. So it's got to be a multiple of V. And I should say that that multiple can be positive or negative or even 0. Okay? So for example, if the vector W happened to be over here, then the projection would be in this direction. That's fine too. Okay, and what does this vector U have to satisfy? Well, here's the main condition here. The difference between W and U ought to be perpendicular to V. In other words, in the diagram, if we join the tip of U to the tip of W, get this vector in green here, that's the vector W minus U because it goes from the head of U to the head of the W. We want this vector here to be perpendicular to the vector V. That's what we mean when we say we're dropping a perpendicular down. That this vector here be perpendicular to this vector here. So the idea is we want to find a vector U such that U is first of all a multiple of V, and secondly, that this condition is satisfied. Let's call it star. Okay, here's the formula. The projection formula is that the projection of W onto V, vector we're calling U, is given by this formula here. And there's two dot products, one in the numerator here and one in the denominator here. So this is a number divided by another number. So that is a number. That big combination is a number. And that number is multiplying the vector V. So we are indeed getting a multiple of V. The multiple happens to be this quotient of V dot W with V dot V. All right, so let's prove this projection formula. So we're looking for this vector U that satisfies these two conditions. And so we know that U has to be some multiple of V. So let's say lambda times V for some number lambda. Okay, so then this perpendicularity condition is equivalent to the dot product between W minus U and V being 0. So that's how we define perpendicularity. Once we've set up a dot product of the two vectors is 0. That's what perpendicularity means. So W minus U, because we're assuming U is lambda times V, dot V equals 0. That's the condition star here. All right, but we know that this dot product is bilinear. So here's a sum of two vectors, actually a difference of two vectors. So this dot product here can be rewritten as W dot V minus lambda times V dot V. So I'm using the bilinearity here really twice. The bilinearity having to do with the distributive property and the bilinearity having to do with being able to pull a multiple out. Okay, all of that's still equal to 0 on the right-hand side. Well, W dot V is a number and V dot V is a number, so we can solve for lambda. So lambda is going to be W dot V divided by V dot V. And I prefer just to write it as V dot W over V dot V. It's the same thing, we're just using the symmetric property of the bilinear form. So that's the multiple that multiplies V to get U. So in conclusion, U is equal to lambda times V. Lambda is this, so we just write it down V dot W over V dot V times V. It's a very important formula. Very important, very useful. In physics, it's very important because projecting one force into a certain direction is something that physicists use all the time to resolve forces. Engineers do this when they're making constructions and have lots of forces acting in certain directions. They have to resolve forces, or sometimes velocities or accelerations, whatever have you. So this is a very useful formula applied in many different situations. So let me make a little remark here. Notice that the W vector only appears once. Okay, so the W only appears there, and all the other places there's a V involved. And maybe it's useful to notice what would happen if we replaced V with, say, 2 times V. If we projected W not onto V, but onto a longer version of V. We should get the same vector out of it, right? Because the projection of W onto any vector in this direction should always be that vector there. So what would happen if we replaced V with, say, 2 times V? Well, there'd be a 2 factor coming from this V and a 2 factor coming from that V. And there would be a 2 squared factor coming from the 2 V's down here. So they would all cancel. So yes, indeed, this is really independent of scaling of V. Not independent of scaling of W, but it is independent of scaling of V. Also, the idea of a projection of one vector onto another, a very explicit formula for that projection in terms of the dot product. That's a very important formula to remember. Okay, so here are some exercises for you to solidify your understanding of this projection business. So first one, find the projection of vector 3, 2 on the vector 4, 1. And then find the projection of 4, 1 on 3, 2. Those will be different vectors. And you can graph both of them to make sure that you're getting the right kind of answer. And here find projection onto 5, 6 of minus 1, 2. Just writing it in different form, and graph that as well. Now a little bit more theoretically, show that if you have the projection onto V of W1 plus W2, that's the projection onto V of W1 plus the projection onto V of W2. And that's also linear in this sense, that the projection onto V of lambda times W is lambda times the projection of V onto W. So also show that if you reverse the roles here, that in general, if we take the projection onto V1 plus V2 of W, that's certainly not equal to the projection onto V1 of W plus the projection onto V2 of W. So it's linear in this argument, but it's not linear in the vector V here. But do show that, and I've already talked about this, that the projection of W onto V is the same as the projection of W onto lambda times V. All right, so an important note that this problem here, 29.2 part 1, shows that this projection onto V, if we think of it as something that inputs a vector W and outputs the vector P sub V of W, that is a linear transformation. That's what these two lines are telling us. That P sub V is a linear transformation. This is linear algebra, so we like to do a little bit of algebra. And often we end up learning more when we not do just computations with specific numbers, but do computations a little bit more generally with variables rather than specific numbers. When you do computations with specific numbers, the arithmetic tends to collapse things, and at the end you cannot see where the ingredients actually went. You just see the final number. When you do algebra with lots of variables, the final answer that you get still sort of encodes information, and its form tells you something. Okay, so we're going to see that here because we're going to look at a formula for the general projection. So we're going to look at a general vector v, a, b, a general vector w, x, y. And we're going to look at the projection of w onto v. We're still going to think of this one as sort of being a fixed vector, and this one as being variable. Okay, but we're going to make this calculation. Here's the formula that we established in the previous slide. It's v dot w over v dot v times the vector v. All right, so it's not too hard to do this. So v dot w is the dot product of these two things. That's ax plus by up on the numerator. And in the denominator we have v dot v, which is just a times a plus b times b. There it is there. And we're multiplying all of that by the vector v, which is the vector ab. Okay, so let's have a look at that in a little bit different way. Let's take this number and actually put it inside the vector, so we get just a vector. So if we take this number and we multiply it by a, then we get a squared x plus aby over this denominator a squared plus b squared. If we take this number and we multiply it by b, then we're going to get over here abx plus b squared y, still over a squared plus b squared. Okay, this common denominator a squared plus b squared, maybe it's more conceptual to bring it out front. Then we can write things a little bit more efficiently as 1 over a squared plus b squared times the vector a squared x plus aby and abx plus b squared y. And now we can see more clearly, perhaps, very concretely, that this is indeed a linear transformation. In terms of inputting x, y, and outputting this vector, we see that the x and y are appearing only linearly here. And indeed, we can rewrite this in terms of multiplying the vector x, y by a certain matrix. And the matrix has coefficients a squared, ab, and b squared. So I remind you, this times this plus this times this gives us that entry. This times this plus this times this gives us that entry. And there's still a 1 over a squared plus b squared out front. So here's a very nice formula for the projection. If you were going to write a computer program that did a lot of projections, you might just use this formula. Given the vector a and b, this is projection onto ab. This is what it does to a general vector xy. Now this matrix is kind of interesting. It's clearly somehow connected with this vector AB. And in fact, it has a very lovely relationship with this vector AB. And so here's something for you to check, okay, an exercise that you can rewrite this in the much more compact form over here. So here's still the vector W, there's a vector xy on the right. But this whole combination here can be written as vector v times vector v transpose divided by vector v transpose times vector v. Now remember, we're thinking of all these things as being matrices, so they don't commute. Right? So the numerator here and the denominator here are not the same. They're involving the same two ingredients, the vector v and its transpose. But on the one hand, we're multiplying v times v transpose on the right, and in the denominator there's a v transpose times a v. So it's different. In particular, v transpose times v is just the dot product of v with v. We've seen that before. And I want you to think about what v times v transpose is. I want you to convince yourself that that is in fact this matrix here. So this is a vector v, which is a 2 by 1 matrix, 2 by 1. And here's its transpose, so it's a 1 by 2. So if you multiply a 2 by 1 by 1 by 2, you should get a 2 by 2, and I want you to check that you get this in here. And another exercise is to then compare this result with actually the original definition. Okay? You might like to think about whether you could have actually gone from here to here directly without any of this intermediate calculation. All right, so it's an excellent exercise to think about. How to go from here to here just sort of with abstract thought without actually making any calculation. This formula is very important to those of you who have done some statistics, you may recognize this kind of thing comes up in statistics. It comes up in lots of other things too. It's a formula that generalizes in lots of interesting directions. Okay. So in our next video, we're going to carry on with more applications of the dot product to planar geometry. Now that we know about projections, it'll be pretty easy for us to talk about reflections. Then we'll talk about rotations as well. So we're going to see the dot product really playing a central role in understanding the metrical structure of the plane and basic transformations of it. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.